Yeah, so maybe a quick intro before we start the main part. I guess if you are here, you already saw our landing page with all the information, but let's quickly recap what this is about. So for a couple of months, we were doing such meetings on a regular basis. These meetings are about discussing the machine learning papers. And this is the first attempt to make such open meeting. But I would say it's still semi-open because, as you can see, we have already chosen the paper that we will be talking about, and you were just invited if you like it. But in general, our internal procedure is that we can all submit papers as candidates for next paper talks, and then we vote for the next session, and the winning paper is discussed on the next session, and the person who submitted that winning paper is starting the discussion, and and we discuss this topic. Right now, we just selected this paper by ourselves, but we want to share the whole thing with you if there is interest. So anyone could submit papers, and we will also do voting and so on. Yeah, but it will happen from the next, or yeah.
That would be definitely interesting, especially if more people vote and more people send
suggestions.
that obviously we have a larger base to choose from, and perhaps we find something even more interesting. So yeah, when talking about the formula as well, like what we found was kind of organic. We just basically read through or even skim read at points the papers, and then had a discussion together to go deeper into some facts and some questions. Like when there is more people, you obviously read through it better. You can answer each other's question, and hopefully we all learn something at every such meeting. So yeah.
Yeah, so the paper that we discussed today is, as you can see, it's about vision transformers. It's also quite unique situation because, as I said already, usually there is one person who submits the paper and then is somehow obliged to start the discussion. But this was the paper that several people wanted to discuss. So Oleg will be the one to start the discussion, but for sure there were more people interested in doing that. So I hope the discussion will be quite lively. So
yeah, we just had a question about if we should ask questions. So yeah, please do. And basically it's a kind of democratic forum to talk about the paper. So even if you're say from outside GetInData, don't worry, just ask any question you want, and correct us if we're wrong. Just feel free.
Yeah, and don't wait until the end. There will be no Q&A. It is all about Q&A. So
yes,
yeah. So interrupt at any time, and let's just have a discussion, not just a presentation.
Yeah, let's have a discussion. Well, at some points we could say, oh yeah, this is gonna be just in the next chapter, so that's when it will be mentioned. But yeah, apart from that, yeah, let's have a discussion. Piotr, anything else?
No, I think we can start.
Okay, so let's start it. I will just basically skim read through most parts of the paper, and then we'll discuss like previously said. So an image is worth 256 words. Transformers for image recognition at scale by Alexei Dosovitsky et alia. I will not pronounce all those names. What's interesting, obviously, they're from Google Research. That's why they had this massive data set that was accessible to them and lots of compute. Even though, as we'll find out, transformers are more efficient than ResNets. as they claim here. While the transformer architecture has become the de facto standard for natural language processing tasks, its applications to computer vision remain limited. Now, well, that was the case 1 year ago. It changed a lot since then. In vision, attention is either applied in conjunction with convolutional networks or used to replace certain components of convolutional networks while keeping their overall structure in place. We show that this reliance on CNNs is not necessary, and the pure transformer applied directly to the sequence of image patches can perform very well on image classification tasks. When pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks like ImageNet, CIFAR, or VTAB, Vision Transformer, VIT for short, attains excellent results compared to state-of-the-art convolutional neural networks, while requiring substantially fewer computational resources to train. So that's the main selling point.
Yeah, I already had one thought while reading this abstract, because it's, I mean, it's quite natural that it's about pre-training on a large corpus, especially if you are talking about transformers, and then doing benchmarks on smaller data sets, because those benchmarks exists. And but I was wondering if, in general, are there any benchmarks on really large data sets to to train the model on a really large data set, and then also evaluate it on similar one? Or
I'm sure there have been benchmarks done where a model is trained on ImageNet and then it's inferred on something else, like out of distribution, and it's also a big data set. I forgot the name of the other set. Maybe someone could help me. It will be mentioned later on as well, I think, one of those sets. But apart from that, I don't know what exactly you mean.
Because I was also wondering if this setup that we are downsizing somehow, training on a large corpus that reflects
corpus,
what you are
right?
doing.
You're still thinking about text.
Yeah, exactly. Yeah, it reflects what you do in NLP. So I was wondering if it doesn't, somehow work in favor of transformers compared to ResNets or something like that.
Wait, so if I understand, so would you like to train the model on a large data set like ImageNet and then have a benchmark on a large data set as well, or did I misunderstand? I feel like I misunderstood your question.
Yeah, I would like to have a benchmark on equally large data set, like train even, to take a half of the very big data set and then test it on.
I'm not sure if it was done. I don't remember right now. We'll go back to the tables and appendices. I might be not exactly sure right off the bat if it was benchmarked on a set like that.
Yeah, usually they were pre-trained on these bigger data sets like this HGFT 300 from Google, but the testing was usually done on these smaller data sets, and usually they are not were not using the full data set, but they were using some few-shot accuracy. So because the testing is very compute hungry, and they were testing it on the smaller data sets.
Yeah, that's true. And now that I remember, yeah, the JFT 300 million is much larger than ImageNet, or 2 orders of magnitude larger, if I remember correctly. And basically, they also said, that's a little spoiler, that it's saturated before the 300 million samples as well. So this data set was even too large. But they did it because they were Google, so they could do it. So why not? Then maybe we would have another result like double descent or something. So they just trained it. Okay, so I'll go through the introduction. I'll try not to read everything just like the abstract, but I decided it's important to read it in full. So self-attention based architectures, in particular transformers, like from the Attention is All You Need paper here, have become the model of choice for NLP. The dominant approach is to pre-train a large text corpus and then fine-tune into smaller tasks. So Piotr, you're asking, usually the idea is to train it on a large model and then That's why they're like benchmarking on a smaller sample, because you want to distill the knowledge. You want to download the weights from someone and then fine tune it. So I guess that's the mainstream application. Yeah. Thanks to their efficiency, transformers have become, it's become possible to train models of unprecedented size with hundreds of billions of parameters, like GPT. I think that's the paper. With the models and datasets growing, there's still no sign of saturating performance like ChatGPT. In computer vision, however, well, convolutional architectures remain dominant. So AlexNet was I think Glennet, and then Hedel was that was Resident, right? 2016. Inspired by success from NLP, lots of people tried combining CNNs with self-attention, but it was usually, I think, like Michał, I think, yeah.
Yeah, it is worth noting that this computer vision was very similar case to the NLP, when first we had only RNNs, then we tried to combine the RNNs with attention, and then there was the transformers architecture where we were using only the attention, self-attention. And we can see that this is similar now with the computer vision models, where we got some good architectures like CNNs, then there was attempts to use CNNs with combination with attention, and now there is people are trying to use only the attention, as in the case in NLP. So here it is one of the first papers that are using the transformers for the images. It is not first paper that people were trying to do it, but it has some highlights that that are only in this paper.
Wait, can you see? I was just trying to annotate something. I'm not sure if you can see that.
Yeah.
So previously you had those convolutional blocks, and then attention, and then convolution and attention, or like, you know, several convolutional blocks and some attention weaved in to weigh how important each outputs are from certain layers, and it would go on. But now we just have attention all the way, so that's why it was called attention is all you need, and now yeah. I need to get out of the annotate mode. Sorry, technical difficulties. One sec. Clear my drawings. I want to get rid of it. Okay, I'll stop sharing and reshare. Yeah, it's a trap. I'll reshare my screen. One sec. Okay, I'm back, I think.
I'm not sure if we want go back to having those meetings via different tools than Zoom.
Actually, I don't know. I think we'll work it out. If Zoom is more, if it's easier for people than Meet. Well, we'll see. We'll see. Maybe we can ask people, right? Let's be democratic as promised. Right. So that's about like the previous approaches with the CNNs, and then it went all the way. I mean, actually, I was also referring to how it happened in the NLPs. In NLP, right, you had the RNNs, and then transformers took over. Also because they were much more efficient, because computation could be done in parallel. I would draw something, but I'm afraid it's gonna kick me out again. But basically, we had well, computation in series and not in parallel. As in, for every token, you had to put it for the encoder, then wait for the result, and would have to go to the encoder again. And in transformers and NLP, it just basically with all the tokens had some embedding, and then those embeddings would go for another attention layer. It would just propagate. It would be much faster because of how GPUs are designed to do parallel computation and matrix multiplication. That's why I'd say dot product attention in particular. So yeah, so that's people were obviously after after 2017, and especially after the BERT paper, people were trying to replicate the success, because transformers were just much better than CNNs. Yeah, I'm not sure if everyone's familiar with, but it's going to be explained later in the paper, I guess, with how.
Yes, and if anyone has any question, go ahead and ask them in any moment. Yeah.
Like there are literally no stupid questions, so do it. Right, and that's one interesting thing that is in the paper is here. I actually forgot to highlight it beforehand, but it says we trained the model on image classification in supervised fashion. From the BERT paper at least, the way they trained the model was semi-supervised. They had text, and some words were masked at random places in the text, like 15%, I think, or 20% of the words were masked. And the task was to predict the right word, the right token that would fit in. But here, it turns out that they also tried that, but it had slightly worse results. That's why they do it in a different way. They just try to train it on, well, not on ImageNet, but on this 300M JFM, JFT.
JFT, probably.
Yeah, JFT set, and this signal comes from the labels. So it's interesting what could be done. Maybe they could try, other tasks or do multitask training, but that wasn't explored, I think, in this paper. Yeah. Oh, okay. So there we go. When trained on mid-sized data sets such as ImageNet without strong regularization, these models yield modest accuracies of a few percentage points lower than resonance of comparable size. Now that they explain it well, they say transformers lack some of the inductive biases like CNNs have. So CNNs, like as a history note, were developed based on the cortex, on the visual cortex, how the cells in our visual cortex are aligned and connected together. Well, roughly, right? Because no one actually, scanned the connections one-to-one, but roughly they're in those grids, right? Just like the CNN filters, and that really helped as as an inductive bias. Also, you had a translation equivariance, and it was local. I mean, that helps because you have weight sharing, and there is a bit less to learn at the start, at least. So yeah, so there is that, and I explain why it's doing worse when on smaller data sets. However, because it doesn't have inductive bias, it has more flexibility to learn, right? So when you unleash it on a 300 million images data set, it can learn everything from scratch. That's where deep learning shines, and that's what they seem to have achieved.
Yes, and this is case with the inductive bias because models usually need some pretty simple assumptions, like in the bias models where we have some prior distribution. It helps model to fit the data set, but usually it can be also harmful because there are some assumptions, and these assumptions are not always true. So for example, where we have some other data set that this prior distribution isn't true, the model will perform worse. So the best
locality,
idea,
right?
yes, like the locality in the terms of the CNNs, and the best way to tackle this is to model to learn everything by itself. So don't say it to it that hey, take this prior distribution, but maybe try to learn it from the data set. But for that we really need a lot of data, and this is where the transformers actually exceeds.
Yeah, that's why I'm smiling, because you were saying that, and while it's true, or it may be true, you have to be Google to really say it with confidence to have this compute. Well, maybe not Google, but you have to have a lot of compute. So yeah.
Yeah, it was also really interesting, and I think we'll get to that later, when they were using those hybrid architectures, when they were using CNNs as backbones, not to feed the transformer with those raw patches, but with already some patches taken from feature maps. and it turned out that for large data sets, it doesn't really help. So those transformers are able to learn equally well from scratch than from some feature maps.
Yeah, I'm wondering what will happen if you did both, right? If you concatenated the image or image patches and also the CNN outputs, right? So then the network would have choice to actually use one or the other, or maybe maybe it will be impractical because of memory constraints or something. I don't know. But you could always have both. And
sounds like some kind of skip connection at the beginning of.
Yeah, actually, yeah, it would kind of be equivalent. Yeah. Yeah, I mean, this is kind of reiteration, transformers, NLP, BERT, GPT. Very good. Donald Trump-esque summary of that paragraph. I think there is not, unless there is someone's comment. Yeah, no use for text, right? Oh yeah, I don't know, for some reason this paper is seminal. They were tried to be used before, but I think it wasn't as generalizable. As we'll find out in this paper, Michał, like this architecture is basically, it's like an adapter, right? If you're familiar with software architecture patterns, it takes those image patches that we'll discuss a bit down below, and after you have tokens from those patches, you can use any kind of NLP architecture, because then images become words. That's why that's the kind of essence of the title, right? An image is worth 16 by 16 words. I get that's also a hyperparameter. It's not always 16 by 16, but yeah, but you've got a grid of image patches, and once you have tokens from them, they're treated linearly, and you can use any architecture. And I think the previous approaches weren't as general, and I guess they weren't as successful, because if they were successful, we would have heard about them a bit more. But that's,
yes. So some of them weren't as general, but some of them were even more general, that they were trying to apply the transformer to the pixels. So
yeah,
here we are having this 16 by 16 patches. So they're for like big image, there is not so many patches 16 by 16, but if we count every pixel, there are actually a lot of it. And because the transformers architecture has actually a quadratic complexity, because the self-attention mechanisms need to attend from each pixel to each other pixel, it's begins the biquadratic complexity, because in the image, which is 256 by 256, we have 256 squared, and then if we will need to apply the self-attention, we'll have another squared, so biquadratic complexity, which is really bad. And this was like pure transformer, but it can be done right now because it is really bad in terms of complexity of computations.
Yeah, I'll just skip ahead a little bit to the patches, because we talked about those patches, right? When we explain that, because we've read the paper, I guess not everyone has read the patches. So I guess we'll go a bit out of order. So this is basically how it works. If you get an image, you split it into little puzzles, a grid like that, and then you feed it linearly row by row. And those are your tokens, like in words. You feed every one of those patches, which I think here will be like, I remember 14 by 14, or for some reason that number pops into my head, but it doesn't really matter. They're like small patches, and they go through the linear projection, and then they go into transformer as tokens. So from then on, you can treat it like in any other architecture, what I said before. And also what's, I guess, I mean, to me, it's interesting, because I'm still a mathematician at heart. You can look at it as a limit, right? So if you had those patches one by one, then you have the naive transformer. And if you imagine you have just one single patch, it will be just like, not a resonant, but just like a deep multi-layer perceptron, I guess, right? It would just go, because then you'd have trivial attention with just one token, and it would just go through. So you have this trade-off, and then depending on how big your patches, you land somewhere in the middle, when where you trade off how efficient it is versus how much attention you leverage. That's kind of my intuition. It's perhaps not perfect, but not sure what you think about that. Anyway, so now that we know about the patches, I guess like is that clear? Maybe there are some questions.
Yeah, I have one thought, but I don't know. You can like to continue or.
Yeah, I'll continue. Right. Yeah, thus we apply transformers in the context of image processing. Several approximations have been tried in the past. As we said, such local multi-head dot product self-attention, that's a mouthful, blobs can completely replace convolutions. And then we have the papers I mentioned. In a different line of work, sparse transformers employ scalable approximation. This is basically about like all the different approximations that have been tried to make it work. And then you had attention only calculated along one axis, for example. Then most related to ours is the model of Cordonier, which extracts patches of size 2 by 2 from the input and applies full self-attention on top. This model is very similar to VIT, but our work goes further to demonstrate that large pre-training makes vanilla transformer competitive with or better than state-of-the-art CNNs. So it's kind of, yeah, we have the same idea, but we have more compute. We'll do it better. Which makes the model applicable only to small resolution images, while we handle medium resolution images as well. I think they do 224 by 224, right? So there has also been a lot of interest in combining convolutional neural networks. I was also wondering, by the way, if those patches could, if it could have like overlap or reorganize them somehow. And has that been done? I think that's not been explored in this paper. I'm not sure. Maybe I've missed it.
Yeah, I just thought about one thing. If we're still talking about patches, maybe it's a good thing to mention, because yeah. I just realized that they introduced some constraint. I don't know if it was just a simplification or yeah, I guess, because the one constraint that you have in when you're using convolutional networks is that you have to resize images to be able to perform all those operations on those input images. So we usually make them square and of specific resolution, like 224, like here, and they did the same thing here. So when they're comparing to ResNet, they are obviously making those square images of 224, and they are doing the same for a transformer. But correct me if I'm wrong, but when you're using transformers in the original setup for NLP, you have sentences of different length. And it's not a constraint that you have to input the same shaped input every time. So I think they are, giving up some advantage that transformers could have, that they could take inputs of different shapes and divide them into those patches.
Yeah, I guess, I mean, especially for inference, right? It would be useful. Actually, I mentioned something like that in the appendix. But what I can say is, yeah, you can, if you have a larger image, you can just have more patches and you will have a longer list of tokens and they will go through as well.
Yes, actually, they were pre-training on. Okay.
Caveats, right? There are two caveats. If you're pre-training on a smaller set and then you put more tokens in, it's all fine. But there is also if someone remembers, I think from BERT, there is a positional embedding, and that was given poor results because it wasn't trained as well. So what they did was basically they had, say, I don't know, in the training set they said they had up to, let's say, 100 tokens, but in fact they fed an image that was large enough or it had, like, I don't know, 300 tokens. So they interpolated the position token based on, well, just I think linearly interpolated, like 2D interpolation. So like, if you had like like a Sierpinski fractal here. Remember, imagine like every one of those patches is also composed of 9 patches. So you would calculate the embeddings between them based on where they are in the position, like based on what the neighboring embeddings are. Is that what you wanted to say, Michał? Or
Yeah,
I roughly remember it. I may have said something slightly wrong. But...
Yes, I think it was like you said, but also in this paper, they said that they were pre-training on some smaller images, but during the fine-tuning phase, they actually used the larger images. So the input actually were bigger in the fine-tuning part of the of this training. So actually, they have used this property of transformers.
Yeah. But then I guess one other thing, like from practical perspective, if you trained on a GPU and you have a certain amount of memory on your card, then you want to have as many tokens as possible, but not too many to not decrease your batch. So perhaps you do have specific like preferred sizes that you want to deal with. You want to have 512 tokens or whatever, right? Or whatever, exactly. Like it doesn't really matter how many, but there is a number, practical number usually.
Yes, especially with such high computational cost and such big data sets,
like
it's very important.
10% speed up is a lot of money, right? When you train something huge. So yeah, so that's the method. We actually went through it before, and this is the how attention works on the diagram. Michał, if you want to go through that, or
yeah, so like the Oleg said at the beginning, we have the image, and then we are creating the patches. So these patches then are like the matrix 16 by 16, but we are flattening to the flat vector that has length of 16 by 16. And after that, we are feeding it to the transformer. What is really important about a transformer, that they are not really using the order of these input vectors. This is different than in case of RNNs, where we are processing each of input in sequential manner. So this is different in terms of transformers, and the other part is that we are adding to each of this patch the position embedding. So it's something that actually models learn how the patches are actually positioned in the original image. But I think it's well explained below in this method paragraph.
Yeah. Okay. So let's go further. Hello.
Hi, I've got a question about the class embedding, I think. Is it similar to BERT model? And second, do we add positional embeddings to this token also?
Yes, this is...
yeah, okay, go on.
It is exactly the same as this sentence and token in the BERT. And for the second question, I'm not really sure if we are adding the positional embedding. I think that below there is a question with that, but I don't know if it is clearly stated there.
Okay.
Yeah, I can't remember either 100%. But yeah, it's very similar, and there were also other methods mentioned, but actually for the same reason of just empirical performance, they chose to go with the class token method.
Yes, and this is pretty important because the output of these transformers, actually, number of outputs of these transformers are the number of the patches that we input into them, but we are ignoring all of the others, but the class token output. So we are using to the classification only that one input, because all of the information is actually somehow put into this one embedding at the end.
Yeah, I guess you could say technically, right, you could cut out the last layer, but you don't do it just for the sake of I guess similarity, right, kind of order.
So we don't use output from the other image patches. So should we do this calculation or just don't do it?
I'm not
guess
really
I
sure
guess
if
because if you do a similar calculations, it's already pre-cached. I guess it either doesn't make sense or maybe it would even make it slower. You know what I mean? Like if you have
Yeah.
15 or like 25 attention blocks one after the other, and then you just use the first token of the last layer, then maybe all the other ones, you know, you could cut it out, but it's also a matrix multiplication. I guess I don't know.
Yeah, it makes sense.
It's probably wasn't worth it since they've not done it, or it wasn't, you know, I don't know. But your idea makes sense. Like on face value, maybe you could save some computation, or maybe you wouldn't. Would have to try it because it's not always as obvious. But certainly, like naively, intuitively, it would make sense, right? You by hand you do fewer calculations. I wouldn't calculate those embeddings at the end, but yeah. In model design, we follow the original Vasvani attention is all you need paper as close as possible. But because they wanted to apply all those, that's comes from above. It's just a list of tokens, and you can use that. An advantage of this intentionally simple setup is that scalable NLP transformer architectures and their efficient implementation can be used almost out of the box. As mentioned before, now a vision transformer overview of the model is depicted below. Standard transformer receives an input of 1D as input a 1D sequence of token embeddings to handle 2D images. We reshape the image of dimensionality high times width times number of channels into a sequence of flattened 2D patches. So we got n patches, and each one has the resolution p squared, right? Yeah, p by p is the resolution of each patch. And then from the resolution, we try to calculate the number and how many patches we have by hw over p squared. I guess I'm not sure if it's implied that the resolution, should divide the height and width or not, or do you do overlap or padding? But I guess that's marginal to our discussion. We'd work it out if we were to implement it, so that's not that important. Which also serves as the affected input sequence length for the transformer. So yeah, larger image, you have more tokens. Transformer uses constant latent vector says D. Was a comment? Oh no, that was just my highlighting. For all of its layers, we flatten the patches and map to the dimensions with a trainable linear projection. So once we have those patches, we just do a linear projection. And we refer to this projection as the patch embeddings. Similar to Bird's class token, as you asked me how previously, we prepend the learnable embedding the sequence of embedded patches X class Z00 to state that the output of the transformer serves as the image representation Y. Both during pre-training and fine-tuning, a classification head is attached to Z0L, so the output of the ELF layer. The classification head is implemented by an MLP multi-layer perceptron with one hidden layer at pre-training and a single layer at fine-tune time. I'm actually not sure why that is, why they had more at pre-training and fewer at fine-tuning, but maybe someone who read it knows or thought about that. I don't know. Okay, I guess not.
What is your question?
About this sentence, right? So they're saying that at pre-training, they had a hidden layer at pre-training, but not at fine-tuning time. I'm actually not sure why. I remember first time I was reading, but I forgot to highlight it. But yeah, I was thinking, why is that? And I don't think it was answered below as well in dependencies or anywhere. So
yeah, I think they have in the appendix that they are fine-tuning only because this MLP is consisted of 2 layers, and during the fine-tuning phase they are fine-tuning only the last layer because it was better, but it's strangely put here into the words.
Yeah, so I get why you only have single layer at fine tuning, because you just want to use the embeddings because you assume they're good, they're like linearly separable, and yeah, they're good enough. But I don't get why there is a hidden layer and how that makes the embeddings below better. But yeah, I guess I'll have to live with that. I don't know why that is. Yeah, position embeddings are as patch embeddings to retain positional information. We use standard linearable 1D position embeddings since we have not observed significant performance gains from using more advanced 2D aware position embeddings. And yeah, I highlighted it because yeah, that was the first doubt in my head. As in, I was wondering, why would you, like, I know the priors and the inductive bias comments we had, but like, I was thinking like, maybe, just maybe even like you'd add something learnable to, and initialize it with like some weights based on distance from one patch to the other, like how far it is or like which direction, maybe you could do at least, at least a few dimensional embedding or something. And they just said, yeah, we thought about it, but it had worse performance. So it was like, okay, that makes sense.
Yeah, I saw that comment that they tried it and it was worse, but they just tried it. Like it's only empirical.
Yeah,
They
maybe they
didn't
haven't tried
say
it hard enough.
why.
Yeah. Oh, yeah, maybe, maybe we should go and write a paper, try it. So the transformer.
Yeah, I think that aligns good with what they wanted to show, that actually that this transformer doesn't need any 2D aware positioning and less spatial information is better for transformers. So maybe that's because of that.
Yeah, but we can wonder like how far they went in that direction, or like.
Yeah, it's quite convenient because it confirms the theory, right? That they didn't provide any proof rather than just comment that
No,
it was
I guess
worse.
this will be implicitly learned later, because you have, in attention you have every token attends to every other token. So then perhaps if we went deep into analyzing how the attention is distributed among the tokens, right? Maybe there would be some correlation that this patch, patch, say if we have 3x3, patch 4 would have high values when you do 4-1 and like 4-7, right? And 4-5 or something like that. I don't know. I'm speculating here because I've not done that, but maybe it's learned in the layers.
Yes,
Both,
but
right?
yeah,
Because I was thinking of a special case that added like a learnable weights, but those weights, I guess, are in the attention because it's like a graph, right? Attention is like a fully connected graph.
yes, for the diagrams from below, we actually can see that this one-dimensional positional and embedding is enough, but it's something in the I think in the end of this. No appendix, but closer to the conclusions, I think.
Yeah. Right. Yeah, but that was definitely one of the interesting parts in this paper. Then they have a layer norm applied, so incremented. Yeah. And we have residual connections. Oh, it's yeah. And this MLP just has 2 layers with Jello. Here we have the equation. So the class token prepended and those other tokens, and then you got you add positional embedding, and then you go through layers, right? So you do that's multi attention, self attention, right? What's MSA for?
Yes, multi-head self-attention, I think. And
Yeah.
it's pretty nice that all of the architecture can be actually put in this only 4 equations, and actually they describe a lot of what is happening there, because
literally this is how to, right? You have a for loop in Python and you implement in PyTorch and you implement it. It would be quite easy, right? Once you have those blocks defined, and then layer norm, and yeah, and that's the strip connection. So there we go. And then you have,
we can
yeah,
actually...
they do it. Oh yeah, because they said MLP after they're intertwined, so interleaved. So that's that, right? I guess. And then you have final layer norm.
Yes, we can actually describe this because maybe it will help somebody to discover what is here. So this Z0 vector first is actually the inputs. So this X class is the class token, as we have spoken before, and every this XP1 vector is actually the patch of the some patch of the image that was flattened, and every this E letter is actually the linear layer that is used to map this this vector to the dimensionality that these transformers
E
accepts.
stands for encoder, I guess, right? That's why it's E. Or
embedding. Maybe embedding, I think. Yeah, so it's only transferring from this space, this size of space, to the dimensionality. And at the end, we are adding for all of this. I think all of this, because it's n+1, so we can answer the Michał question. We are adding this embedding positional embedding to all of these inputs. So also to the X class, because here we have +1, I think.
Yeah, you can
and
say, like you
then
could
we
literally
are
implement it in NumPy, right? Concat or like PyTorch, right? Concat,
yes,
and you have
the first
EPOS, and the dimensions agree, right? Times the p squared times c, that's n. This is n+1, but then you have, right, that's e, but e multiplied by that, how many times, and then you have +1 here. So the dimensions agree, and you add it up.
The first step is pretty easy. Then we are just going like L times through the multi self attention and MLP, and in some times we are applying this normalization. But
that's what's so interesting about attention, right? Once you know it and you've heard about it, it's like, yeah, why wasn't it discovered earlier, right? Anyway, yeah, sorry, did you want to continue? Did I?
No.
Okay.
I think.
Yeah, we know that vision transformer has much less image-specific inductive bias than CNNs. We already said it like 3 times in this paper. Sorry, I don't want to read the same thing over and over, so I'm just skim reading with the cursor.
Yeah, by the way, we have 9 minutes left, so keep in mind
but
to
we're almost
get to the result, because this is, I think, the most interesting part, that they really did it.
Really? Not for me, but yeah. I like this part as well. But let's go. Yeah, and in VIT, only MLP layers are local and translationally invariant, while the self-attention layers are global. So as we said, like, it goes everything attends to everything. The two-dimensional neighborhood structure is used very sparingly in the beginning of the model by cutting the image into patches at fine-tuning time for adjusting the position embeddings for images of different resolution, as described below. Other than that, the position embeddings at initialization time carry no information about the 2D positions of the patches, and all spatial relations between the patches have to be learned from scratch. Then we have this hybrid architecture. We've actually discussed it briefly before. So this is about having some embeddings from CNN, some pre-trained CNN or just CNN at the start, and then it would feed into some layers of attention. But that's another approach, but it wasn't really explored as much. Was it? No, it was, but I think it yielded worse results. Actually, sometimes they say something and don't, like, you have a question in your head. In this paper, like several times I noticed something and they don't say it's in the appendix, but this is in the appendix, and they explored it and they had worse results. So it would really be nice if they said, oh yeah, look at the appendix. So typically we train VIT on large models and fine-tune to smaller tasks. For this, we remove the pre-trained prediction head and attach a zero initialized D times K feed-forward layer, where K is the number of downstream classes. It's often beneficial to fine-tune at higher resolution than pre-training. When feeding images of higher resolution, we keep the patch size the same as before, right? As we discussed before, which results in a larger effective sequence length, some more tokens. The vision transformer can handle arbitrary sequence length obviously up to memory constraints. However, the pre-trained position embeddings may no longer be meaningful. And there comes the interpolation trick, right? We therefore perform 2D interpolation of the pre-trained position embeddings according to their location in the original image. Note that this resolution adjustment and patch extraction are the only point at which an inductive bias about the 2D structure of the images is manually injected in the division transformer. So the patches, and this is the only other point, right, where they do the interpolation. So that's based on the location. We evaluate the representation learning capabilities of resonant vision, VIT, and the hybrid approach. To understand the data requirements of each model, we pre-train on datasets of varying sizes and evaluate many benchmark tasks. When considering the computation cost of pre-training the model, VIT performs very favorably, attaining state-of-the-art and most recognition benchmarks. Well, that was 1 year ago, so prehistory, but let's continue. At a lower pre-training cost. Lastly, we perform a small experiment using self-supervision and show that self-supervised VIT holds promise for the future. I said the prehistory jokingly, but actually, even if you download like Stable Diffusion, it will have the best models. Backbones will be based on Vision Transformer, so it's up to date. As in, it's still used. That's kind of why we chose it as well. To explore model scalability, we use this version of ImageNet, 1K classes. I guess, Piotr, do you have any interesting, especially because you found this part the most interesting, and we only have 5 minutes,
No,
maybe you give the most interesting remarks, or?
Nothing, really.
Okay, out of the ordinary.
Yeah, but interesting is the part that is interesting is that they really did those benchmarks on several data sets, and you can show this table on the next page, I guess.
Oh,
yeah,
this one? Oh, the big one.
No, the other one. Yeah, this one. So yeah, so the interesting part is that they just have proven it really on several data sets that at the time when on most data sets this huge ResNet was state of the art, and on some other data sets it was efficient net. They have beaten them all, so it really looks nice that they really proved that it works. So, and also as you can see in the last row of this table, it's not only they achieved comparable or better results, but they also did it with less computation costs. So yeah, they made their statement really, at least in this setup and on those benchmarks. But as you said, this line of work continues, and there are other confirmations that it's a correct direction. So
yeah, it's kind of a seminal paper, right? Kind of like, I don't know, clip, and then based on that you had DALI, or like, yeah, there are many papers. I guess many architectures use it. Does anyone remember? Because I actually forgot what the noisy student was about. We would have to read. Okay, I guess I'll read it if no one remembers. I'll read later because we're running out of time. We've got 2 minutes. I guess it's. There was not supposed to be any Q&A, but I guess if we have a few more minutes, maybe we can stay a bit longer if someone has any questions at the end. I guess with those results, we should cut like the kind of lead part of the presentation, even though it was discussion all the way through, but there is not enough time to start a new kind of official part. We'll just not go through it. So yeah, that's that. If you're interested, or if you want to go through the appendices, let us know. We could do a follow-up, or we could go and study a different paper next time. There is still a bit some interesting stuff. I guess I'll do like a 4-year-old approach. I'll go through the images, you know, show us the images that you can. I was wondering, like, I haven't seen at least those images. I just quick comments like how we could do perhaps like object segmentation or not. I'm not sure if that was kind of tried, but I'm not sure with Vision Transformer. Was it with this paper exactly, or with some follow-up?
It was pointed out somewhere as there were some attempts, or they planned some attempts, but not in this paper for sure.
Yeah, I think it was further down the line, but obviously I've not seen them in, you know, in synchronous order. So I guess, yeah, this is all the equations about multi-head self-attention. It's very well done. This paper actually, it's self-explanatory, and the appendices are always where a lot of interesting stuff lies. But there was one more figure that was quite interesting, and it was not this one. I think it was this one, and basically they had the class token approach that Michał asked about, right? So this is the curve. I think this accuracy curve and epochs, and the blue one is for the class token approach, and then we've got green and orange, and they're so they said initially. Oh, so the other approach is based on, I guess, what was it with the gap? Yeah, just average pooling. Yeah, just using the patch embeddings and averaging them, and on that making the predictions. So that was not as good, but then they decided, oh yeah, that was just the wrong learning rate. So yeah, so some approaches are worth reconsidering. And with that, I'd like to finish and thank you for your attention. Yeah.
Yeah, because the attention is all you need.
Yeah.
Okay,
Bye.
so Claudia, are you there? Would you
Have
like
the
to
last word?
wrap up?
Yeah. Thank you all for coming to the first meeting. I hope you enjoy it, and we will be able to meet again probably after New Year.
Yeah, definitely.
Yeah.
So thank you.
Thank you.
Bye.
Bye.
Thank you. Bye bye.